Hi, dear friends. Hope you are all well. Here today, we will see in this video, we will see the order of integers in the modular arithmetic, where you don't have the ordinary operation like addition, multiplication, subtraction, and all that. And we will continue this. We will see through this modular arithmetic, or you can say through these order of integers in modular arithmetic. We will see the converse of Fermat's theorem. Okay, first I will introduce the Euler's function phi. We have the function phi from set of natural numbers to natural numbers, which is defined by phi of any integer m is equal to number of integers less than or equal to m and relatively prime to m. For instance, if you see value of phi at say 4, the number of integers in this set 1, 2, 3, 4, which are relatively prime with 4, that's only 1 and 3. So the number of such integers is 2. Phi 4 is 2. Similarly, you can see phi of say 6 in the same set 5 and 6. For 6 you have only 2 and 5, which are relatively prime with this 6. So phi 6 is again 2, and so on. You can calculate for all values of this m. Now, if we have, in fact, we have a result. If m is, or you can say, if p is a prime number. If p is a prime number, then phi of p is equal to p minus 1. That's obvious, because if you select prime here, then every integer to the left of that prime is relatively prime with that p, because prime number does not have any divisor other than the number and 1. For instance, if I take phi of 7 up to 7, if we calculate phi 7, every integer to the left of 7, positive integer of course, every integer to the left of 7 is relatively prime with 7. So there are 6 such positive integers, so this is equal to 6. Of course, this means the number of positive integers less than or equal to m, which are relatively prime with m. Now, we have also the converse of this. If for some integer you have phi of m is equal to m minus 1, you are calculating phi m for some integer m, and that turns to be m minus 1, then m is definitely a prime number. M is a prime number. So this result is, in fact, if and only phi of m is m minus 1, if and only if m is a prime. You can see the proof of this. I think it's very simple. It's not too difficult. I don't want to discuss its proof here. Now, with this Euler's phi function, there is a result. There is a theorem known as Euler's theorem, which says if you have any integer, if a is a positive integer, in fact you can take any integer, but here I am interested with the positive integers only. If a is any integer, any positive integer, and m is 1, where m is some integer, then a power phi of m is congruent to 1 mod m. Means if you raise this phi of m to this a and subtract 1 from that very integer, that integer will be a multiple of m. I hope we will have the knowledge of this congruence. We say some integer a is congruent to some other integer b modulo m if m divides a minus b. You might have the knowledge of this congruence and all properties of this congruence. Now what Euler's theorem says us, this is a power phi of m is congruent to 1 mod m, provided a and m are relatively prime. A and m are relatively prime. So this theorem guarantees us the existence of an integer which is here phi of m, such that a power phi of m is congruent to 1 mod m. Now let me list the sequence of powers of a. Consider this sequence. Consider the sequence a square, a cube, so on. I will choose this sequence, all powers of a. This sequence is definitely a periodic sequence. A power 4, so on, a power some n, a power n plus 1, and so on. This sequence will be definitely periodic sequence. You can see how this is true, because by Euler's theorem we have one of the integer. Phi of m is definitely some integer, because in fact a natural number, it's a function from n to n. So this will be some integer, some natural number. So in this sequence you will definitely get somewhere 1, because you are taking all integers, 1, 2, 3, 4, so on. So powers are exactly the natural numbers and phi m is a natural number. Somewhere you will get 1. Okay, if I choose some integer, say greater than phi of m, say I have in this sequence I have a power, say some t, which is greater than phi of m. Then I can divide this t by phi of m. I can write that somewhere I have a power t in this sequence. This t can be written as phi of m into q plus r by using division algorithm. I am dividing this t by phi of m. Then this r will be, r is less than or equal to, in fact subtract less, phi of m and greater or equal to 0. Now if I calculate a power t, what is a power t? That will be a power phi of m into q into a power r. But a power phi of m by Euler's theorem, because I have a and 1, so a power phi of m will be 1. So this will be 1 power q congruent here into a power r modulo m. Means a power t is congruent to a power r modulo m. So I can say that when I construct this very sequence in modular arithmetic with modulo m, this sequence will be definitely periodic. After some stage, this will come, this will repeat, because you have r, a power t. T was some integer bigger than phi of m. Here t has this r has restriction. R is greater or equal to 0, but strictly less than phi of m. So this will, a power t is equal to a power r, but r is less than phi of m. Means after this phi of m, it will exactly repeat. So I can say possibly I can have some integer other than phi of m in this sequence, such that a power that integer is congruent to 1 by m, because this gives the existence, this theorem. So I will define the integer belonging to a given exponent. Okay, let me write definition here. If a is a positive integer, and am is 1. Am is 1. Then a is said to belong an exponent t modulo m if a power t is congruent to 1 mod m, or you can say if t is a least positive integer, t is a least positive integer, if t is a least positive integer such that a power t is congruent to 1 mod n. So t must be a least positive integer. Now you can say whether this t will exist or not. The Euler's theorem says that a power phi of m is congruent to 1 mod m, provided m is 1. Here I have m 1, so by Euler's theorem I have this very integer. But this theorem does not tell me that this phi of m is the smallest positive integer with this very property. Now I am selecting t to be a least one. If such t will not exist, then at least I have phi of m. So t is a least positive integer such that a power t is congruent to 1 mod m. If such a t exists, then we say a belongs to an exponent t modulo m, or in other words we say t is the order of a modulo m. We also say order of a modulo m is equal to t. That is the notation, order a modulo m is equal to t. So Euler's theorem gives the existence of the order of that very integer. So what is the order now? Simply, if you have a and m 1, a and m is 1, GCD of these two is 1, you determine the smallest power of a, some t, such that a power t is congruent to 1 mod m. Smallest such t. Such t will definitely exist because of Euler's theorem. Euler's theorem says a power phi m is 1. But Euler's theorem does not say that very phi m is a least integer. Possibly that can be bigger than t. Or sometimes that is itself a least integer. In that case, in fact, a is also called the primitive root of m. Okay, let us say some examples. Suppose I choose a equal to 3 and m equal to 4. Clearly 3 and 4 is 1. I want to calculate the order of 3 modulo 4. So I have to find smallest t. A power t means 3 power t must be congruent to 1 modulo 4. If I choose 3 power 1, 3 power 1 will be 3 modulo 4, because 3 minus 3 is 0, is divisible by 4. If I go to 3 square is equal to 9. 9 is congruent to 1 modulo 4. So I have 2, the smallest positive integer, because before 2 you have 1. 1 does not satisfy this very condition if all t is congruent to 1 mod 4. So smallest such t is here 2. 3 square is congruent to 1 mod 4. So I can say order of 3 modulo 4 is equal to 2. Because I have 2, the smallest one. Similarly, you can select only those a's which have GCD 1 with the integer 4. So you can now select say 1. 1 power 1 is congruent to 1 mod 4. Implies order of 1. Order of 1 modulo 4 is equal to 1. This way we can calculate the orders. We can take some other examples. Say m is equal to 5 and a is equal to 2. What is the order? Order of a modulo m. You have 2 congruent to, you should have 1 here. So 1 is not the order, because 2 power something must be congruent to 1, and that thing must be least. So what is 2 square? 2 square is 4. So 2 square is congruent to 4 modulo, here m is 5. Modulo 5. 2 cube. 2 cubed is 8, is equal to 8. 8 is congruent to 3 modulo 5. 2 power 4 is 12. 2 power 4 is equal to, I'm sorry, here it is 6, multiply both sides with 2, it is 6. 6 is congruent to 1 modulo 5. 6 is congruent to 1 modulo 5. So I can say, therefore 2 power 4 is congruent to 1 modulo 5. Implies order of 2 modulo 4 modulo 5 is equal to 4. So this is the order of 2 modulo 5. Order of 2 modulo 5. Now in this case you can see there is no any integer smaller than 4. For example, for 1 it is 2, for 2 it is 4 here, for 3 it is 3 here, for 4 it is 1. So smallest positive integer t in this case is 4. 2 power 4 is congruent to 1 mod 5. Means in this, if you calculate phi of 5, that Euler's theorem says, because m and 2 have GCD 1, so Euler's theorem says 2 power phi of 5 is congruent to 1 mod 5. But you know, phi of a prime number is prime minus 1, so it is 2 power 4 congruent to 1 mod 5. So in this case 2 power 4 is congruent to, means you have Euler's theorem here. So you don't have any integer smaller than the integer given by Euler's theorem. Smallest integer is here, the integer given by Euler's theorem. That says a power phi of m is congruent to 1 mod m. So here the phi of m is 4 in this case. So the order of 2 modulo 5 is equal to, order of 2 modulo 5 is equal to 4. Now suppose you have, we will do this simple exercise here. If you have two integers a and m such that m is 1, and you have a power u congruent to 1 mod m. Suppose you have some integer by default, you don't know what u is actually, is this smaller than phi of m or bigger than phi of m. Some integer you are getting, while simplification you are obtaining some integer u such that a power u is congruent to 1 mod m. You want to see what can be the relation of this u with the order of a, because order is the smallest such t, smallest such u you can say, but here you don't know what u is. Maybe there may be some integer smaller than u such that a power u is congruent to 1 mod m. So this exercise says us, if this thing happens, you have two integers with a and 1 and a power u is congruent to 1 mod m, then what is the order of a? Order of a will be among the divisors of u. So this actually reduces the labor of calculating the order of integers modulo given number. This is very simple. For instance, I will choose order, let order of a modulo m is equal to t. Then you know t is the smallest, then t is smallest. T is smallest integer. T is smallest integer such that a power t is congruent to 1 mod m. This is smallest. But here we don't know whether this is smaller than t or not. But here you have t smallest such integer. Means t must be bigger than u. Otherwise u is itself the order. So here you say t is the smallest integer such that a power t is congruent to 1 mod m. So what must happen? I can divide this u by t, because t is bigger than, this u is bigger than t. So using division algorithm, I can write u is equal to t times q plus r, where 0 is less or equal to r is less than what? The divisor t. But I claim here this r must be 0. If r is not 0, if r is not equal to 0, then you can see what's a power u. A power u will be a power tq into a power r. This I can write a power t power q into a power r. But a power t is congruent. A power t is congruent to 1 mod m. So this is 1 power q, that's 1. So that's a power r. That's a power r modulo m. So you have a power u congruent to a power r modulo m. So a power u is a power r congruent to a power r modulo m. But this very r is smaller than t. But you say t is smallest positive integer with this property. But here you are getting a power u is congruent to a power r, and r is smaller than t. So this is clearly a contradiction to the fact that t is smaller, because you have u congruent to 1 mod n. So you are getting u smaller than you are getting u smaller than t, but you are here dividing u by t. You are dividing means you are assuming that u is greater than t, but here you get u smaller than t because r is smaller than t. So you must have r equal to 0. When r is equal to 0, therefore r is 0. That implies from this relation u is equal to t times q, which implies t divides u. In the division algorithm, that q is also integer, q and r are integers. So t is dividing u. That means order of a. What is actually t? Order of a modulo m. That's dividing u. That's what you have to prove. So this actually this component is the solution of the problem. So order of a modulo m is among the divisors. From this I also get one of the interesting property. See, this is the first exercise. Second comes trivially from this one. If am is 1, then I can say order of a modulo m divides phi of m. So this will tell you what can be the order among the divisors of phi m. Order is among the divisors of phi of m. How this follows. In fact, a of m is 1. So here a of m is 1. By Euler's theorem, a power phi of m is congruent to 1 mod m. By Euler's theorem. By Euler's theorem, a power phi of m is congruent to 1 mod n. So in this case, phi of m is congruent to a power phi of m is congruent to 1 mod n. Now this exercise says if am is 1 and a power u is congruent to 1 mod m, then order of a must divide u. You have exactly the same thing. You have am1, you get this by Euler's theorem. So you have am1 and a power u is here phi of m. This is congruent to 1 mod m. So by this exercise, you can say this implies order of a modulo m divides phi of m. Very simple. Order of a modulo m divides phi of m. So the applications of this in calculating the order, for example, you have to calculate the order of, find order of all integers less than or equal to, say, 17 modulo 17, because every integer less or equal to 17 is relatively prime with 17 except 17. So all means you have to calculate the order for first 16 integers. Phi of, for example, you choose a to be for the first integer. 1 is always 1 power 1 is always congruent to 1 modulo 17. 1 has order 1. For 2, what can be the power? 2 is congruent to what? 2 must be congruent to 1 modulo 17. 2 power something. What that power must be? This term says us that power must be among the divisors of phi of m. Here m is 17. What is phi of m? That is 16, because 17 is a prime number. So phi of 17 is 16. So order of 2 modulo 17 must divide 16. So you should try here only for 1, 2, 4, 8 and then go to 16, because those are the only divisors of 16. You should not calculate 2 power 5. Don't discuss about 2 power 7. Don't discuss about 2 power 9, because order divided 16, order of 2. The only divisors of 16 are, so order I can say order of 2 modulo 17 must be among, modulo 17 must be among is either 1 or 2 or 4 or 8 or 16. In fact, you can check one by one which will work here. This is how to calculate the order of an integer modulo a given number. Now we will see the converse of this very well-known theorem, Fermats theorem. You know, this theorem says if p is a prime number and p does not divide an integer a, then a power p minus 1 is always congruent to 1 modulo p. It's a p. A power p minus 1 is congruent to 1 modulo p. This is a well-known result. I want to see the converse of this. So what will be the converse? Converse is if you have this type of relation, a power p minus 1 is congruent to a power some m minus 1 is congruent to 1 modulo m, is m prime? This is the question. So converse is converse holds better, but that holds under a given condition. It is if you have a power m minus 1 congruent to 1 modulo m. So this is exactly this. This must imply this very p is prime, but there is one more condition on this relation, and a power m minus 1 over p is not congruent to 1 modulo m. Where? What is p here? Where p runs over prime divisors of m minus 1. If this congruence will not hold, where this p is a prime divisor of m minus 1, then m is prime. Then m is a prime number. So if a power m minus 1 is congruent to 1 modulo m, and this congruence does not hold, where p runs over the prime divisors of m minus 1, then m is a prime number. Let us see the proof of this converse. Again, let me choose the order of a. Let order of a modulo m is equal to t. Then you know t is the smallest positive integer. Then t is smallest. T is smallest positive integer, such that a power t is congruent 1 mod m. Now you have given congruence here, a power m minus 1 is congruent 1 mod m, and t is order. It's exactly what we did in the last exercise, that if you have a power u congruent 1 mod m and a power t is okay, there's one more question here. First of all, what about the GCD of a and m? Because when we talk about the order, we have always GCD 1, but here you have a power m minus 1 congruent to 1 mod m. There is in fact one result which you can see at your own places. If a is congruent to b modulo some integer m, then the GCD of a and m is same as GCD of b and m. This one. This is very simple. You can see it at our own places. You have these two. We call this as a, this as b. Now this a is congruent to this very b modulo m, so you can say a power m minus 1 is congruent to 1 mod m, means GCD of a, I will have a power m minus 1 and m equal to 1 and m by this very congruence. This implication will tell me that this congruence implies this, but GCD of these two is 1. So GCD of these two is 1. Now a power m minus 1 with m is 1. You must have a and m 1. So I can talk about the order. So I will suppose here, so this is in fact, this trivially implies here a and m are relatively prime. Now let me suppose order of a modulo m is this equal to t, then t I have a smallest positive integer such that a power t is congruent to 1 mod m. T is smallest such integer. So by the last exercise, we must have, this implies t divides m minus 1. T divides m minus 1, which means m minus 1 is equal to, say, t times l, where l is some integer. I will show this l is actually 1. If I show this l is 1, then I will get order of a modulo m is exactly m minus 1. And we will use Fermats theorem, this Euler's theorem, to get the result. M minus 1 is equal to t times l, where l is some integer. If l is bigger than 1, if l is greater than 1, then I will choose a prime divisor of l. Then p divides l is a prime divisor. Then choose a prime divisor p of l. So p will divide l, means l I can write as some k times p. Some k times p, where k is some integer. K is some integer. K is some integer. This will imply from this very equation, I get m minus 1 is equal to t k p. That means m minus 1 by p, m minus 1 by p is equal to t times k. Now you can see here, a power t is congruent to 1 mod m. Now let me calculate here a power m minus 1 over p. This is equal to a t then power k. But I have a power t congruent to 1 mod m. So this will be congruent to 1 mod m. This will be congruent to 1 mod m. Because a power t is congruent to 1 mod m. You have 1 power k, that's 1. So a power m minus 1 over p is congruent to 1 mod m. Means you have contradiction to this very given hypothesis. Because you are choosing p a prime divisor of l. Since p divides l and l divides m minus 1, means p divides m minus 1, means p is a prime divisor of m minus 1. So p is a prime divisor of m minus 1, and you have a power m minus 1 over p congruent to 1. Means you have this type of congruence, a power m minus 1, which is exactly congruent to 1 mod m. So you can say we have a contradiction to the given hypothesis. Means this L cannot be greater than 1, because whenever it has a prime divisor, that gives us against to this. Means L must be 1. When L is 1, you will have, so L must be 1. So you can see this implies L is equal to 1. When L is 1, I have m minus 1 equal to t. So order is m minus 1 is equal to t. Means I can say order of a modulo m is exactly equal to m minus 1. But order of a modulo m divides phi of m. As we have seen in the last exercise. So you get m minus 1 divides phi of m. Divides phi of m. But that will imply m minus 1 is less than or equal to phi of m. Because m minus 1 is a divisor of phi of m. But by definition of phi of m, phi of m actually counts. Phi of m counts the number of integers less than or equal to m, which are relatively prime to m, means phi of, obviously m is not relatively prime with m because m and m is 1, GCD of m and m is 1, sorry m, means m and m are not relatively prime, means when you calculate phi of m, it is at most m minus 1, means phi of m is always less or equal to m minus 1, but phi of m is always less or equal to m minus 1. Combining these two will imply phi of m is exactly m minus 1. This I told you in the introduction that when phi of m is exactly m minus 1, then m is always prime number. So m is a prime number. Means when you have a power m minus 1 concurrent to 1 mod m, you cannot directly say that m is a prime number. So the converse of Fermats theorem holds, but under additional condition. And if you have a power m minus 1 by p not congruent to 1 mod m, where p runs over the prime divisors of m minus 1, then m is a prime number. This is actually the converse of Fermats theorem. Okay.